Hello, good afternoon. SPI training. All right, so agenda. What is SPI? SPI bus signals, SPI timing diagram, and multi-slave bus. And forewarning, some of the terminology is questionable, but here we go. What is SPI? Serial Peripheral Interface is what it is. So it's a high-speed communication bus, and you can go up to 24 megahertz and beyond. Now I have an asterisk there because you can get up to about 24 megahertz and still have a good and reliable signal. If you go past that, then you're likely to have issues if you don't design your communications buses with signal integrity in mind. So the recommendation is to not exceed 24 megahertz. Okay. Next, SPI is full duplex. What I mean by that is you have the MOSI line and the MISO line. That's how the two devices communicate with each other. And full duplex means that as one device is communicating to the other device is communicating back. And that's a requirement, not a condition. In order for the transaction to happen, they both have to transmit synchronously. Okay. So SPI is a 3-wire bus. I say 4 because you'll also need a chip select or a slave select. And that's where I mentioned you might see some questionable terminology. The device that drives all the other devices is called master device, and the other devices are called slave devices. Okay? And so the way this all works is basically we're working with a circular buffer. As the master device writes data out 1 bit at a time, that bit gets shifted into the slave device's buffer, and the slave device's last bit gets shifted back to the master. And that's how they exchange that information, and after 8 cycles, the 8 bits are exchanged, that full byte is exchanged, and the transaction is complete. Okay. Next slide. So, SPI bus signals. So, as I mentioned before, we have MOSI and MISO. MOSI stands for Master Out, Slave In. This implies that it's driven by the master out, so the data is coming out of the master. It is being sent from the master to the slave device, slave in. So MISO is the other way around. It's driven by the slave, so the slave sends the data out and is received at the master from the slave. In order for the transactions to be synchronized, we need a serial clock, which is the S clock. Okay, so the S clock is driven by the master. This synchronizes both the MOSI and the MISO lines. Then we have the chip select or slave select, and so that is also driven by the master and activates the slave's MISO line. This implies that MISO is high Z until the chip is selected. Okay, that's important to note. If the slave is not selected, the output from the slave is high Z, and there's nothing to read from there. Lastly, let's see if I can get rid of this. It's kind of hidden there.
You're gonna keep your mouse. Just use the space bar.
There we go. Okay, got it. Thank you. Last to mention is the interrupt. It's not always present on all slave devices, but this can be used as an interrupt signal to your processor that you can then acknowledge. And that is, of course, driven by the slave device. Okay. So to talk about the timing diagram, first couple things I should talk about is clock polarity and clock phase. So clock polarity, that determines when the clock is idle. So when clock polarity is 0, it's idle at 0, and the cycle starts with a positive edge. When the clock polarity is 1, the clock idles at 1 or high, and the cycle starts with the negative edge. Then clock phase determines when the devices transmit and receive. With a clock phase of 0, transmit changes at the trailing clock edge of the current cycle. So at the current cycle, at the last clock edge, that's when the transmit changes. And so transmit, again, both MOSI and MISO lines are being transmitted because we're full duplex. Both slave and master are transmitting. RX captures at the leading clock edge of the next cycle. And this will make more sense when we get to the next slide. For a clock phase of 1, it's the other way around. Transmit changes at leading clock edge instead, and receive captures at trailing clock edge instead. Okay. So again, we have our red, which indicates the leading edge, and a blue, which indicates the trailing edge. Okay. Let's see if I can turn on the pointer. There's the pointer. So this is the start of our first clock cycle, and then this is the end of our first and the start of our second clock cycle. Okay. When clock polarity is 0, that means we do our clocks with the positive edge at the start, and it goes down. And then this is our second clock cycle, again with positive edge. With clock polarity of 1, it's the other way around, negative edge instead. Okay. So, with a clock phase of 0, that means we are capturing on this leading edge. This is when we capture, which implies that the moment we have our chip select or slave select, we are already transmitting. Okay. We transmit, and at that first clock edge, that's when we receive. Okay. For clock phase of 1, instead, we transmit when the clock starts. Okay. So that distinction is important to know. Okay. And I put the two diagrams together just so that you can refer to it later on with the diagram and the annotations. So here's an example. This is with clock polarity 0 and clock phase 0. Clock polarity 0 again, pause edge clock. And this is when we capture. Okay. And then this is an example with continuous transfer, basically multiple transactions with your SPI. Okay. So this is the first transaction. Chip select is activated, and so this is active low. And then this is our second transaction here. Okay. Another thing to note is that, as you can see in that length here, 4 to 16 bits, so that means SPI can transmit at any at various lengths of bits, and it's restricted only by how the SPI device is implemented. And in our case, I'm implementing our SPI module right now for 8 bits only, but that can be expanded. Okay. One more thing I wanted to talk about is the concept of multi-slave buses. So you can have one SPI bus and multiple slave devices communicating on this SPI bus. And there are a couple topologies for this. The first topology is with independent chip selects. And as you can already tell, that can become cumbersome if you have too many slave devices with multiple chip selects expanding out. Okay. The other option then would be to daisy chain. And with daisy chain, you have only one chip select, but the way that you would separate out each device would be through time. What I mean by that let's take a look at the timing diagram for a daisy-chained multi-slave SPI bus. Okay, so here it is, timing diagram for this daisy chain. We have one chip select again. The idea is, as you transmit from one device, that device will transmit to the next device, and that device will transmit to the next device. And so that also implies that your transaction, instead of 16 cycles with one device, becomes 16 times 3 cycles. So it's longer. Okay. So this is the trade-off. If you don't want to use too many chip selects, the trade-off is your transactions need to be longer. Okay. So after you send those 16 times 3 cycles, then you deassert your chip select, and that will then allow the devices to interpret the packet that is sent, that they have received. Okay. So we can consider these as instructions, 32-bit instructions for each of these devices. And at the point where we deassert, they then interpret these instructions. This is a block diagram for the SPI module that I am implementing. So besides the SPI-specific wires, the chip select, the S clock, the MOSI, and the MISO, we have clock and reset, and then we have enable. So the enable, this activates the SPI to perform the SPI transaction. Then we have the output enable, which outputs the last received packet onto this data bus. The write enable is then what is used to input the next transmit packet from the data bus. Okay, so this implies that this data bus, this port here is bidirectional. Okay, it's an input and an output. Next, we have clock polarity and clock phase. Again, this determines the polarity and phase of our S clock. And then we have our busy, which is a busy flag telling the processor whether the SPI module is currently working on a transaction. And then the done flag tells the processor that the transaction is complete. Then finally, again, this data bus is the port to the data bus of the microprocessor. Okay. That's all I have on the SPI training for now. I am still working on the SPI module. There are a couple things that I'm still debugging. In a couple hours, I should be done with that, but I'm going to say more likely sometime this evening around 8 p.m. is when it'll be published to the GitHub. Okay. Any questions from the folks in the room?
Is MISO usually used for like checking that your data like transferred correctly?
No.
Or what? Because it looks like on slide 3, it looks like you shift over one bit at a time, and then MISO like shifts its most significant bit back to the master.
That happens at the same time.
Okay, so as you're shifting over a bit, it's shifting over
yes.
the same bit?
It's not shifting over the same bit, it's a different bit.
Like these two have different values, and as you're transmitting one, you're receiving a different value.
So you're receiving like the value that you were sent 7 clocks ago.
The idea is that it's
new data is loaded into that register for the slave, and as that transaction occurs, new data gets sent to the slave and gets read.
Right. So, for example, you might have a temperature module that communicates over SPI. So that temperature module has a register that holds the temperature value. And so the idea is that that temperature value is written to that register, And when the SPI transaction